Check it out now, y'all.
nanoHUB-U, online instruction.
All right, welcome. We'll be discussing a solution of the homeworks today. And hopefully you found the homework not too difficult. But as you're working through the math of the problem, a few square roots here and a few one line of algebra, 2 lines of algebra there, I hope you will not get lost on the basic meaning that why the homework was assigned to begin with. What is the connection with the lectures that we had, and why did I really choose those problems rather than a completely different set? Let me explain that in these few slides. By the way, if you have other questions that you really cannot solve, send me a note, and certainly I'll be able to go over those problems also. So this is an opportunity for discussion. So in the whole set, you will see that there are about 12 problems or so, 11, 12 problems. And I only asked you to make your life easier, only a subset of it. And the idea was that the first problem will get you comfortable with the numbers, like the headache medicine, a millimolar concentration versus micromolar. This is not a unit that we use every day. And so therefore, getting comfortable with this molar concentrations is very important. That's 1.1. 1.3 is really there to see whether the answers are reasonable. You see, a job, once you have taken a course, is not the knowledge per se, but some sort of intuition that what is right, what is wrong. You should be able to say even when a book is not around or the courses are not around. So I'll try to tell you about that at 1.3. 1.6 tells you how to cheat the system. Meaning that how to sort of look up capacitances and immediately sort of get the final answer in a few lines of algebra rather than really solving complicated diffusion capture problem. But the point I want to emphasize is that when you're using this capacitance table, you have to be a little bit careful, because if you're not careful, you can pick up a completely wrong value, although it looks almost the same. I'll tell you a little bit about, I had been using approximations in various places. You may be uncomfortable. I'll show you one. And then this is very important. Biosensor lab program essentially will tell us, it will allow you to exercise your various types of designs so that you know what the final answers are. In problem 1.3, I asked you to calculate two quantities. That if you have a cell of a certain size, let's say a micron size cell, how long does it diffuse in 10 minutes versus if you had a little protein, right, 1,000 times smaller, let's say, how far does that one diffuse? And you know that since it's a small molecule diffusing in 3 dimensions, so the diffusion distance is 6 dt. Now this 6, of course, is a prefactor, and dt, so you get the diffusion coefficient. The diffusion coefficient is given, and the time is 10 minutes. So you can immediately see that the protein would go about 629 micron, a long distance, I'd say. On the other hand, the cell will almost not move at all. This is a big thing. So it goes only 18 micron within the same 10 minutes. Now that makes sense. A big cell will be repeatedly scattered, and so therefore it cannot go very far, and a little one will be more mobile and it will go much farther. That's fine. But you see, this brings us to a very important point. Remember when I said a femtomolar concentration? Femtomolar concentration is that in a volume, in a box volume of 100 micron by 100 micron by 100 micron, you have one biomolecule. Let's say very low concentration. Now, let's say your friend has just done an experiment with the cell and is very excited and has come to you and said that this is the response he's getting. Response is a function of time, and he's getting a big signal and he's very happy about it. Now, you look at this and you see that that's about 10 minutes when the signal begins to rise. And the person said that he's doing an experiment with a cell, with a bacteria. Now, what do you think should your response be? Your response should be that it is essentially impossible that a molecule starting from a random place would travel 100 micron within 10 minutes and give you a sensor response. probably this experiment, there's something else going on. This experiment is most probably not right. Now, if your friend did the same experiment with a protein, well, it would then go about 600 microns. So there is at least some chance that the experiment would be right. So this analyte volume is important and sense time is important. This is the back of the envelope thing that one should always do before you read any paper on this field or do any sensor calculation or look at any sensor response. You should always look at where the time starts and do a quick back of the envelope calculation to say that whether it's possible or not. That was 1.3. That's why I asked you to calculate the diffusion distance. Very simple, but it was hopefully very important. And then the next problem in 1.6, we asked that if you have created a new biosensor which has a disc shape, so like a penny or like a quarter, it has that shape, and you're trying to capture biomolecules on it. What would be the response? Now, I told you everything about spherical sensors, nanowire sensors and all. How are you going to do it? Well, you can immediately go to Wikipedia. Wikipedia has a list of capacitances, or you can just Google capacitances and you will get a result. So I'm asking you to do 3 different things: calculate the steady state diffusion, and then be a little bit careful about how you use the capacitance formula and interpret the result. So let's start here on the first part, and you'll see it in your solution also. So let's say when you go in Wikipedia, it will tell you the capacitance, electrostatic capacitance is 8 epsilon A. And you're doing steady state, 1 disk in infinite media. Well, you know the rule. Change epsilon with D. No problem. So that's the diffusion equivalent, diffusion coefficient, replacing epsilon. But when you look at this number, you should be very careful. You see what that table said, yes, it is a disk capacitor, capacitor, but it is sinking flux from both sides. It is getting flux from here, and flux is also coming from the bottom. Your sensor, however, was sitting on a table, and therefore, or in the bottom of a beaker. So flux was only coming from one side. So if you use this formula, yes, it is from Wikipedia, that was quick, but it is slightly wrong. By the way, so if you use this CDSS formula for a disk sitting in the middle of a solution, then very quickly you can calculate the total flux, which is rho times the analyte density multiplied by CDSS. And if you wanted to calculate the total number, you'd simply multiply with time t. In 10 minutes, it will be multiplied by 600 seconds, let's say. So that's not a problem. But this problem is not what we ask you to solve. Now here is the problem. You see, you could immediately see if the disk is sitting on the bottom of a beaker, then flux would only come from one side. So you could say, okay, no problem. Flux are coming from this side, I'll put it in a capacitor, and flux is coming from the other side, I'll put it in a capacitor. 2 capacitors in series. Now, you know already the total value. 2 capacitors in series. What should be this value? 2 capacitors in series will give you 16 dA, and you'll be completely wrong if you use 16 dA. Why? Because you see, in this system, at infinity, the potential is 0. And the potential is finite, quote unquote potential is finite at this point. So there's one point here, and these 2 points are connected. So those 2 capacitors are actually in parallel. They are not in series. And therefore, what will happen, that this problem, the original problem, when you do it a half plane, the capacitors are in parallel, and therefore the capacitance is really half of the original value. And so your answer is 4 AD. If you got that answer, you should be happy, because that's essentially what I was looking for. Now, why is this flux larger? By how much? Well, if the flux towards a spherical sensor sitting on its own, surrounded by the fluid, is 4 pi dA. If you had the equivalent disk sitting there in the middle of the fluid, it will be 8 dA. And so the ratio will be pi over 2. Why pi over 2? You can see that because the sphere has a little bit larger radius, flux can come normally from all direction. A flat plate, flux can only come normally perpendicular to the surface. Little bit low area, smaller area, and so therefore the flux is a little bit less. But in general, if you want to see one-sided, compare it to one-sided capture, then it will be pi. And because in that case, one has the full volume for capture, another has only half the volume. So the ratio is pi. Just a little bit careful, because you see, this is not a dramatic difference. It will not completely change your conclusion, because this is a factor of pi or 2. These are not significant numbers, but still good to be careful so that you know what you're doing. In problem 1.8, which was the third problem, I asked you to sort of look at the exact solution of a spherical sensor, where the molecule is being captured from all sides. This is the flux density at every point, totally integrated. Everything is analytically no problem. In the approximate one, you may remember that we had the transient diffusion equivalent capacitance epsilon was changed by D, and W was, so it was W plus A naught. The W was replaced by 6D, square root of 6 dt, and we calculated the corresponding total capture. Now, if you look at it carefully, these two, to me at least, doesn't look similar at all. I mean, there is no 4 pi sitting here. There is a square root of 6 dt in both places, but the arrangement of A naught is completely different. Is there any chance that these two results would be anywhere close? It turns out that they actually are very close, and I want to explain why they are close. Because just by looking at the math, you would not know that it should be close. The reason it is close is because, by the way, first, did you do the calculation? We did this expanding sphere. Depletion was going on of the analyte concentration, replaced R with square root of 6 dt. And then we simply integrated it for reasonable amount of time, so when this factor becomes small, and that gave us the final answer. So why does it work? The reason it works is because it's the exact solution and approximate solution. The blue line and red line, look, they are on top of each other, essentially indistinguishable. Why? Because what happens that there might be small difference at a very early time when A naught and 6 dt square root plus A naught are comparable. As soon as you have a little bit, let's say 2 A naught or 3 A naught or 4 A naught, remember A naught itself is very small, then this term will drop out. And once this term drops out, then there is essentially no difference between any of the formulas. And therefore, you can see the exact and the approximate one, yeah, there might be small difference in the very beginning, but the disappear factor will disappear very quickly. And you see, if you look at the total number of particle captured as a function of time, you cannot tell them apart. Now, one thing I want to tell you that many times I was not very careful with 6. Sometimes I used, for example, 2. And especially if you had a fractal dimension, what do you use? Do you use 4 or 6? Because it will be somewhere in between. What would have happened if I made a mistake and I replaced it with a factor of 2 rather than 6? Would really things fall apart? Now you can see that with a factor of 6 and a factor of 2, you do have a small difference in terms of transient flux. But if you look the area under the curve is total amount of flux as a function of time, look at the integrated area, then once again you will see that there is almost no difference. The reason is, yeah, with the square root of 2, the transition point where it goes to the infinite limit becomes somewhat weaker, somewhat different. So therefore the curves are slightly different. But the area under the curve essentially gives you a total capture. You will not see much difference. So therefore the approximations we did was actually pretty good. You shouldn't worry about too much whether these results are correct or not. These will turn out to be pretty nice. Very good. Now, the third problem I want to look quickly into is this nanoHUB exercise using Biosensor Lab. And I asked you to calculate a Nanowire sensor with a bunch of information was given, how the molecule comes in, what is the dissociation rate, what is the capture rate, what is the dissociation rate, a bunch of information was given. That's not the essence of this problem. The problem is that you will do a calculation, you will see how the nanoHUB biosensor lab work goes. The important point is this. I said in the salt solution, after 10,000 seconds, which is a couple of hours, the sensors get destroyed because salt goes through the oxide and it destroys the transistor, let's say. In that case, what will be the practical limit of sensing? So this is what I really wanted to know. The basic calculations are not a problem at all. So, you know, these instructions are all given, and so hopefully you were able to follow that. You went through different panels and essentially chose the cylindrical sensor, chose appropriate parameter. So first was the sensor structure, then types of simulation to be done. You chose the appropriate value for Kf and Kr from the table, and receptor density 1e20 × 12. So you put this in, and the values that you don't know, you can keep it at default. And then you did the simulation. And the simulation was done at the ambient condition at 300 degrees C, because diffusion coefficient and other things there do depend on those. And then you do the type of simulation you want to do. So you take this bar, push it to the left because you want to do settling time. Later on, we'll be doing sensitivity or selectivity. We'll be doing homeworks based on by pushing this panels to the left and right. So we'll be doing a lot of homework based on this, but basic idea, very simple. You take a look at this, and then you do the simulate, and you get a curve like this. Now, the important point I want to make here is that you'll get a curve, lower analyte concentration, longer settling time, slope is approximately 1. You remember, right? That this has to go with 3 minus df over 2. df for nanowire is 1, so therefore the slope has to be 1, right? Okay, so this is known. And look at this 10,000 seconds now, because the sensor will be destroyed at that point. And at 10,000 seconds, you go down and look at the minimum analyte concentration that you can see, and you can see below 10 femtomolar. You cannot go below 10 femtomolar because the sensors will be destroyed. And anybody who reports a value lower than that would be it's not a believable result. But actually, it turns out the situation is a little worse than that. Do you remember that I said that in order to know the density, you have to be able to know at least probably 90% of the sensor response, how long it takes. Now, if the sensors get destroyed after 3,000 seconds, in order to get 90%, you actually probably going below a picomolar with confidence should be difficult, right? So this is something I want you to be very careful about, that these type of limits and using this curve in the proper context, interpreting them in the properly, is very important to do the detection limit. Otherwise, you will incorrectly say that there is a limit, but that limit, actual limit, may be actually significantly larger. Finally, I want to return to one problem that I didn't really tell you about. This is problem 1.2. The problem 1.2 simply asked to calculate the diffusion coefficient of a bacteria of a size 1 micron. And this is a very interesting example because I always use this number to remind myself that what the diffusion coefficient of a biomolecule is. And once I tell you, you'll always remember, hopefully. So this is how it works. Very quickly, I'll do a quick derivation to show you what the diffusion coefficient of a molecule is. You may remember that if you have an electron, if you apply a force, the force is Q times E, and the velocity it gets is mu times C, that's the drift velocity. If you take a ratio, you will get a relationship between mu and Q. We know from the Einstein relationship, D over mu is KT over Q, sort of rhymes. And if you use this relationship with the previous one, then you will see VD over F is D over KT. Now here, you see this relationship, VD over F, D over KT, is not only true for electrons, it is true for everything. Anytime you apply a force, it doesn't even have to be charged. And therefore, there is another version of Einstein's relationship through the Stokes equation, that if you have a little sphere in a fluid and you're pushing it, and it is moving it at a velocity Vd, then the relationship between force and the velocity is given by this proportionality constant. That's the diffusion coefficient. And this friction is called F, so you can combine them, and that gives you this 1 over F. d over kt is 1 over F. So as soon as you know F, then you actually know what the diffusion coefficient is. And in this particular case, for this little sphere, F is 6 pi eta A. And you can calculate this, all these values are known. Kt is known, 1.38 10 to the power minus 23 multiplied by 300. A, remember, we are talking about 1 micron bacteria. So A is 10 to the power minus 6. Eta is known. It is 10 to the power 3 kg per meter per second. Put it in 2.2 10 to the power 9 centimeters squared per second. So that's the diffusion coefficient of a bacteria. That's how fast it moves around. Now let's remind ourselves of this table and look at the relative diffusion coefficient. Here is my bacteria, remember 1 micron. So my bacteria diffusion coefficient is 2.2 10 to the power minus 9. And in general, the diffusion coefficient of any molecule is 2.2 10 to the power minus 9 divided by 1 over A when A is measured in micron. So D over A is always a constant. So the way I remember diffusion coefficient is this. A micron-sized bacteria has a 1 nanocentimeter squared per second diffusion coefficient, and a nanometer-sized protein has 1 microcentimeter squared per second diffusion coefficient. So they go in the opposite direction, as you might expect. And so therefore, you can calculate the protein diffusion coefficient using this formula. You can use the cell diffusion coefficient using this formula. And once you have done that, you will be able to say how far they would diffuse in solution for a given time. Let's say 10 minutes, how far they will be able to go. And these values are all known. This is the viscosity is all known from, for water. These values are all known. Now this is a very, so this F, it looks like once you know F, then you know everything. So for example, for sphere, I told you how to get we know how to get C, but there is this strange analogy that if you know the capacitance, then you know the drag coefficient. All you have to do is to replace D with eta and 4 by 6. What about a disk? I told you a few minutes ago, 8 dA if it's a floating disk. All you have to do is to replace 4 by 6. So 8 will become 12 and D with eta. Again, as soon as you know that, as soon as you know the capacitor, you know the drag force and you know the diffusion coefficient. And if it is like a DNA, which is an elongated thing, then the capacitance you can look up 4 pi dA log of 2A over B. A is this radius at this size and B is on the other side. And all you have to do is, to get F, is to replace 4 by 6, D with eta, and you are done. And so this is the strange part, that whether it's a bacteria or a DNA, it turns out that once you know the capacitance formula, you can then find out a whole set of things. And this is really because underneath all these equations, whether you have a Poisson equation, whether you have a diffusion equation, whether you have a fluid flow equation, underneath there are all this second order differential equation. Nature prefers second order equation because you see, if you don't want to perturb the solution too much, fourth order perturbs it too much. And so therefore, when you want to conserve energy, you like second order differential equations. So nature uses it in many contexts to solve its problem. And therefore, the solution turns out to be pretty similar. So therefore, once you have solved one problem, it turns out you can just translate it in all these other languages to give you insights about problems that you thought you had no idea about. So let me stop here. And if there are other problems you would like to know, please drop me an email and we'll work them out. That should be pretty interesting. That's it. So hopefully we'll now go to the second week's lecture, and we'll work out more complicated ways of, or efficient ways of beating all the diffusion limit that we discussed in the first week's lecture. That's it. Thank you.